Okay, so hi everyone. My name is Matt Krjanowicz, and I'm a software engineer. I work on the Windows Server team. And for the last little while, I've been working on sharing virtual disk files among multiple guests. Okay, and so that's what we're going to talk about today. As part of that, we're exposing a new protocol that's built on top of SMB3 called the Remote Shared Virtual Disk Protocol, or MS-RSVD, if you're looking at the shorthand. Okay, I'm going to talk about some background, so some of my assumptions about where we're starting in this conversation. I'm going to talk about some background about how the protocol came out in the scenario that we're looking at solving. Then I'm going to dive into session initialization, some of the metadata and tunneled commands that we go through. And then I'm going to move on to reads and writes, cover some more sort of edge cases of this, talk about session termination, and then that'll be it. There should be plenty of time for questions, and I'm going to pause periodically to ask for questions, so please don't be shy. Ask questions throughout. Some things I am going to get to later on, so I'll tell you if that happens. Okay? So let's first talk about the scenario that we're trying to solve. So in this picture, we've got two virtual machine hosts, host and host here, and three VMs, VM1, 2, and 3. And these three VMs all have OS disks, and for purposes here, I just put them on the hosts, okay? And they've got their local OS disks, okay? This is the model that we know and that we share in Hyper-V today, where you've got a VM, it's got some number of disks attached to it, okay? What we're moving to is a model where the VMs, 1, 2, and 3, all share the same view of a certain amount of storage. And so in this case, all three VMs, 1, 2, and 3, have access to all three of these disks through some sort of shared mode. Okay, this is a file server. Here are hosts. There's SMB between them. And on top of that, there's this protocol that we're going to talk about today. So this is the picture that we're fitting into. It's between hosts and file servers, and in the context of VMs and shared virtual disks. Now, because this is a block protocol, and I'll get to what that means in a minute, we use some block terminology. So I'm going to talk about initiators, and so that's the VM. And I'm going to talk about targets, and those are these disks here. So if you're familiar with the SCSI protocol and so on, initiator and target makes sense. Furthermore, whenever we say data in or data out, it's all relative to these targets. So in means writing data, out means reading data. So the protocol, like I said, is built on top of SMB3. This means that we use SMB3 for all of our discovery, all of our transport, all of our authentication, authorization needs. All of that happens through SMB3. The user configures files. So from that perspective, we get SMB3. I mentioned that there are these block semantics on top of file semantics. So when I say block semantics, I'm talking about virtual disks. So we're actually exposing blocks of the disk to the initiator, but we're using it through SMB. So we're using regular read and write and FS controls and so on. So the block semantics are these blocks of data as well as SCSI commands, and the file semantics are read, write, FS controls, so on. Okay. Finally, this is client-driven. So like SMB in this case, we're only talking about the parts where the client initiates actions. So there isn't like a back and forth. There isn't a push or push notification type system. It's purely the client does something, the server responds to it. Okay, let's talk a little bit about session initialization. So like I said, we're built on top of SMB3. So when the client wants to start to the server, this happens in this black box. And for purposes of everything here today, I'm going to leave SMB as a black box. And I'm only going to talk about the things we do on top of it. So there's this black box. It does authentication, authorization. It does any of the route discovery it wants to do, the multi-channel stuff. All of that stuff still works. And then we get a create file request. Okay? This create file request we respond to, and then we get some starting information. I'm going to talk about the details of this create first, and then later on I'll talk about the details of this getting starting information. So let's talk about what a shared VHDX open actually is. And I should step back and say, I use the acronym SVHDX, that's shared VHDX. VHDX is just the name for the Microsoft file format for virtual hard disks. From the protocol perspective, there's a couple areas where this plays into, but mostly it's just short nomenclature. Okay? We append an alternate data stream. So every open you'll see will have this alternate data stream, shared virtual disk. Okay? We also attach an extra create parameter to the create. So create file requests have some information stored with them. They've got like file attributes, and they've got access, and all that type of stuff. They also have EAs, so extended attributes, that are blocks of data stored that come as well. There's also another dimension called extra create parameters. And this is sort of another sort of list of data that's there. So that's described in the SMB protocol. Okay? You'll either see us open, and I say us in this case, in the client, will either open in read attributes, read control, or in read data, write data mode. So those are the two modes. In this mode,
yeah, sorry to interrupt.
That's
so
okay.
I have to ask, since you're using a data stream, what does this mean for REFS? I mean, is this simply, I mean, there's a backing store question here, and more in terms of if alternate data streams are going to start to see more usage. Is this, you understand why I'm asking?
well, I mean, I guess, so the question is what does it have to do with REFS?
No. REFS does not support data streams, the last I read. Has that changed?
You know, I don't know, but in this case, this still works with REFS. So
Okay.
in the server, we
That's
capture
good to
this
know.
before it gets to REFS.
Okay. And then there was one question. You mentioned something about extended attributes, and I missed the context. Were you just saying about extended attributes were allowed and associated, or are you actually using EAs on as part of the open?
Well, we do both. So they are allowed. We do pass a application ID and an application type EA that describes this. It gives a GUID of the initiator. So for the application ID, and the application type is as virtual disk traffic, just like you see in virtual machines today.
So is that required? Because the only other Microsoft applications I was aware of that used EAs as of today was like the SFU, you know, store and create modes or things like that. I mean, so my impression was that EAs were being deprecated across the board, and I'm wondering if that's, if I misunderstood.
I don't know if you've misunderstood. I don't know the answer to that part of the question. I can say that we're using the same EAs that the underlying virtual disk storage uses in a non-shared case. So we're not adding.
Okay.
Hold on. Let's. Yeah. Let's do that. Thanks.
So there are two pieces, two things here, right? One is the EA, another one is the ECP, right? And EAs are something that we use for CCF, and other parameters are passed over ECP. So in this particular case, you know, we are primarily using ECPs to pass the information, which is very well supported. Right. Yeah, the EAs that we are using here is an existing EAs, right? We are not introducing a new EA. You see what I'm saying? Okay.
I mean, so I guess there's a couple questions here I've heard, right? One is, are EAs deprecated? I don't have a good answer for you on that one. The other is, do we use the EAs as part of this protocol, and are they required? And the answer there is probably no, depending on the server version and how it handles the application ID EAs that exist today for SMB. Does that answer your question?
Good enough for now.
Okay. All right. So we'll move on. And I'll get into the details of what this extra create parameter looks like. Yes, sir. Actually, let's.
So I'm asking, I'm kind of trying to figure out this additional suffix that going into the file name. It's really an ADS the way it used before. So if I go into actually NTFS and open up the file through Notepad, will I see anything like shared virtual disk behind this file?
If you inspect the files on the disk, you will see this ADS there.
So it's actually going to, it's not like something like
Data does not go there, but the ADS
of,
is created. Yeah. Mm-hmm.
Okay. Then of course the question, how is it going to work in REFS? That's
Okay. We'll take that question offline. It actually is sent down to disk in this case. Okay. So let's move on just a little bit. We don't support any sort of caching or buffering on this transport. Okay, so you'll see no intermediate buffering. And then you'll always see a separate connection establishment from the Microsoft client to the Microsoft server. So SMB has this concept of redirecting client connections to a scale-out file server based on where that physical disk is located on that scale-out file server. And right now, in current versions, that mechanism works depending on whether that background storage supports direct I/O. So whether that disk can be directly written to from each node in the file server. In this context, shared virtual disks don't support direct I/O, so all connections have to go to this metadata stack owner, so the disk owner.
Are you saying this only works with cluster shared volumes?
From the Microsoft implementation, yes. This only works if you've got cluster shared volumes in the backend. Other servers can choose to do that. And so the question is, does this work only with cluster shared volumes? And so the only Microsoft server solution that this is supported on is cluster shared volumes.
And last that I knew, REFS is not supported by cluster shared volumes.
So the other question is that REFS is not supported on cluster shared volumes. And I can't answer that question, so I'll get back to you later. OK, let's dive into this ECP, the extra create parameter. This is the GUID for your information. It's here. It contains a client version. So this is the version of the client right now. It's 1. It contains an initiator ID. So this is the GUID of the VM, but it's just a unique ID that identifies the initiator. The host name, so the host from where it comes on. Okay, and in the Microsoft Server implementation, the initiator host name is used for logging and diagnostic purposes. So in our event logs, you'll see this initiator on this host caused this error or something like this. So it'll help admins diagnose what's going on. Some flags describing the open. And so these are flags that say whether it's a metadata open or a read-only open or an open for full access. Okay? And that's described in the spec, as well as flags describing where the open came from. And so the only flags that you'll see here coming across the wire are one flag that says it's coming from the Microsoft Shared Virtual Disk Client, so it's called PVHD parser, or if it's coming from VHDMP, which is the component that parses virtual disks. Okay? And then
hey, Matt,
yes.
This is Tom Talpe. I just thought I'd mention to the people there that some of these changes are not visible in the preview document that we published. They are coming out in a subsequent preview, but some are, well, I'm not sure which ones, but you may want to double check. Some of these things are not present. We can get you the information through other means.
Absolutely. That's worth saying. So this is how it's going to look when we release, to the best of our knowledge, not how it looks at the preview that's available. So we've made some changes to the protocol, and we're happy to work. If there are issues about going between the two, I'm happy to work and get the information out there, the specific differences. But for this, I'm describing how it is now and therefore how it's going to be when we release, to the best of our knowledge. Okay? And finally, this request ID. This is also used for diagnostic purposes. So this is not a globally unique number. It's not even required to necessarily be increasing or non-random or non-conflicting. It's just a number that helps identify where things came from. OK, so that's the session initialization, right? So that's the create file. At this point, you've sent a create file. It's got the ECP. The server has processed it. They've returned a success code to the create file. Okay. Now, the client can do any number of operations on this disk. The disk is available for full access or attribute access, depending on how you opened it. And so you need a way to access this metadata. So we do this through what we call tunneled operations. Now, a tunneled operation is an operation that happens through an FSCTL, an FS control, that does a specific thing, either on the disk or reading about the virtual disk. Okay? This is the FSCTL name. We can get you the number if you'd like. And they've all start with a header. Both the request and response for all of these start with a header. It starts with an operation code, so I'll be going through all the operation codes we support right now.
Actually, I think in the document this is called shvdx_sync_tunnel_.
Yes, that's probably true.
Yeah, just to clarify with the doc.
Actually, no, sorry. From the document, it's RSVD at this point. I took that from the document, from the preview protocol document. The status code is a field set by the client. So if the command reaches the server, the status code for the FS control is going to be status success, unless there's a buffer too small or something like that. So once it reaches the server components, at that point, we fill in the status code here and send the response back. So clients tell the success or failure of the operation based on the status code set here. So I've shaded this blue throughout. If things are shaded blue, they're things that are sent as part of the request but filled in as part of the response. Okay? Request ID, again, there's a number here. Same semantics apply. It doesn't have to be global. Doesn't have to be increasing, used for diagnostic purposes. And then some variable length payload. And the payload changes depending on the request or response. Okay, any questions about this before I get into the specifics of each one? Go for it.
Maximum size is still limited by the maximum negotiated size of the outputs.
Yes. Exactly. So the question is the maximum size as negotiated by the SMB protocol? And the answer is yes. Before I go into the details, I'm going to talk a little bit about versioning. You'll notice there was a client version in the ECP. So in the extra create parameter, the client says, hey, I'm version 1, 2, 3, or 4, so on, whatever. The server can know this. In get starting information, which is the first tunneled operation after the create, which I'll talk about in just a minute, the server identifies its version. And then the server later on, when it gets operation codes it doesn't know about, so that are too big, it returns a version mismatch error code. So that's how versioning is handled right now. So let's start with the get starting information. This is a tunnel FS control that's called immediately after create file. So the session is not considered initialized until this FS control fully is sent and responded to. And it's used for versioning, getting layout of the underlying virtual disk, things like that. So what this looks like is that header. So that same header from before with the operation code, the status code, request ID, and so on. And then the server fills in a server version, so the version of the server, the sector size. So this is the virtual sector size of the virtual disk. So if it reports 512 sectors or 4K sectors, so on. Physical sector size is the sector size of the underlying storage on which the disk is located. These don't have to be the same, right? This can be 512, this can be 4K, this can be 512, this can be 4K. They don't have to be there. This is controlled when the administrator does the virtual disk on a Windows server right now. And the virtual size here is the virtual length of the disk. So a 64 terabyte VHDX file will respond 64 terabytes here, and it might be 512 bytes here and 4K here, for instance. Okay? So again, this is the first tunnel control. You'll see it after client initialization. It'll create file, it'll call this, and then it's good. One thing to note, this is cached. So these are, in this version of the protocol, these are all static or assumed to be static. So the client doesn't need to keep requesting this. And there isn't a mechanism right now for the client to requery this and update its cache. Okay. The next thing I'm going to talk about is SCSI command requests. I'm assuming that you're familiar with SMB, and I'm assuming you're not familiar with SCSI. So SCSI is a protocol between an initiator and a target, and it's got command requests. The command requests contain of a CDB, or command data block, that contains an operation code, as well as some block addresses and a few parameters, depending specifically on the operation code. And these are of variable length up to a fixed length, right, up to a maximum length. They also contain various input and output buffers, and that's all described in the SCSI specifications, and that's kind of a big nebulous topic. So I point out two specific specifications at the end of this, SBC3 and SBC2, and I'll get into what those mean at the end, that I think are particularly informative for this protocol. So at this point, key points, CDB, command data block, has commands, as well as there's a separate buffer that contains parameters to those commands. Returning errors is different. SCSI has a whole bunch of error code, error type data, and it's a multi-level type data thing, and I'll get into that much later. So the command request, again here's our header, right? This is the length, so it's the length of the actual request here. So that includes both the data command descriptor, the CDB, as well as the actual parameters. This is filled in by the client. This is filled in by the server. This data in is a flag, whether it's going data to the server or to the target, or from the target, blank. These flags are described in the spec. I think they're all 0. Data transfer length is the length of this data buffer. So length, everything, data transfer length is the amount that the initiator is requesting be transferred. So therefore, it's the length of this buffer. One thing to keep in mind is this data should be considered untrusted. So these lengths, some of these flags, all this type of stuff comes from the actual guest. So from a trust domain boundary, guest, untrusted. So you're going to have to validate that the buffers are big enough and so on the server side. The CDB buffer describes a SCSI command, and it's in SCSI command parlance, and it follows that spec. So it's network byte order, all that jazz. It's all there. Okay. The server is to process that, and then asynchronously or synchronously send a response. The response, again, contains header, length. SRV status is one of the SCSI status codes that has to do with whether the whole block of command that came through it, so the SCSI request block, whether that command was a valid command or not, or whether that command succeeded or not. Generally, it's OK or error. SCSI status adds a little bit more information and actually has to do with how the underlying command was processed and some of the outputs there, and what those commands mean are described in the SCSI specification. CDB length remains as was set from the server. Sense info length. So sense info is yet more error information presented by the SCSI spec, and that can be returned back. And that describes this buffer here. And I'll get into what that buffer means later. Flags remain unchanged. Data transfer length is the actual amount of data that is returned or was written appropriately. So that's a lot of information that's really dense. Any questions about this so far? No? OK. All right. So moving on, and I'm doing these in ID number order, so they might seem a little weird. There's a check connection operation, and this is issued periodically at the client application request. So client application, meaning whoever's running the VM, or if a user does it through a commandlet or however they want to do it. It generally happens periodically, and it checks the health of the connection. So it checks the health of the actual connection to the target, as well as whether the disk itself is still valid. So you can imagine a case where you start on the create file, start loading the disk, start bringing it up and maintaining your internal structure so that you can start writing to the disk, but something fails after you succeeded the create file. This is your opportunity to make sure the disk is currently accessible. And that type of scenario can happen with a Windows server. So it behooves the client to send this to make sure that the disk is still there, right? So you might see a lot of I/O errors, or you can do this and say, oh, OK, the disk is in an invalid state. It's pretty simple. It just returns the status code in the header. OK, get SRV status. I'm going to describe this. I'm not going to describe why we do it. All right. This is what we use to get our extended status information. And let me be clear. I'm going to describe why we do it later. Same header. And then these are keys and SCSI status and SRV status. This is all the same that I described before. Status key is another thing defined by the SCSI spec. OK, metadata about the disk. The disk, the virtual disk file, can have more metadata about it than what we just get in the starting. And this happens at client request. So for example, if you call get VHD, or you right-click on a shared virtual disk, and then you say inspect this disk, the size of the disk on the file and so on, that's all handled through this tunneled command. And what that looks like, I didn't do a good job shading this one. I'm sorry. The header gets sent down. And then as a response, the disk type, format, block size, and so on gets sent back. Disk type, and I want to make sure I get this right. So disk type in this case is whether the disk is fixed or dynamic. So a fixed disk is one that's described as being fully provisioned. And a dynamic disk is one where you can imagine it's thinly provisioned. So the actual data can change thinly provisioned. The disk format for this protocol is VHDX. And there's a number that's associated with that. It's the only format that's supported in the Microsoft protocol or in the Microsoft implementation. And so if you've got a Microsoft client or Microsoft server, it's going to expect VHDX. Block size is the block size on the disk. So it's a description of how the file is laid out on the disk. The linkage ID is a GUID, and it can be used to ensure that disks that are related to each other are still in that same valid relationship. So we don't support differencing disks as far as this protocol, but imagine that you did. And in that case, the parent differencing disk. So if you've got one disk that's saying, I'm a difference of this other disk. So I've got this block of data here, and this other disk describes, okay, instead of that guy, I'm 43 at block offset 5, and I'm 57 at block offset 10. Well, when that underlying data changes, that might corrupt the client that's looking at the differencing disk. So the linkage ID is used, and it's changed whenever the disk changes, but only after they've detected, or the underlying implementation has detected that it's worth changing it. So it doesn't change on every I/O, but if there's a relationship already established, it can change when there is I/O on there. Okay. Is mounted is whether the disk is valid for I/O on this specific target. Okay. So the disk can be sort of initialized but not mounted, and you can do metadata on it. Or once it's mounted, you can do full I/O on it. The file size is the bytes of the disk, of the file on the disk. So if it's a disk that expands as you grow, so a thinly provisioned disk, then the file size will also grow. And then the virtual disk ID is a GUID again. This one is static. This is the GUID of the disk. It can change, but not while any of this protocol is online. So for the purposes of this protocol, it's static. This is also the same GUID that we use to generate the SCSI page 83 data. So in SCSI, there's essentially pages of information data, essentially sections of metadata. One of those pages is a unique identifier, and it uses this GUID to generate that unique identifier. Okay. Any questions about this? Vinod?
That's the identifier. On the server side, however the implementation is, the page 83 can be implemented based on this ID or any other ID.
Sure.
Right? It's not.
Okay, so you can also ask to validate the disk. So client applications can say, hey, go check this disk and make sure that it's really valid. A good example of when this might happen is if the disk is opened in a mode that it's not fully mounted. You can imagine that maybe you don't want to check the entire file format of the disk and read in hundreds of megabytes of data, supposedly. This will go and do that, and make sure it's valid. And it returns a Boolean saying, yes, it's valid, or no, it's not valid. Okay, any questions about any of these commands so far? Awesome. Let's move on. I'm going to talk about reads and writes. So we talked about SCSI commands, and SCSI does have the ability to do read and write, SCSI op read, SCSI op write, and so on. There are some limitations there, as have been pointed out. FS controls have a certain size. In addition, FS controls can't take advantage of some of the other benefits of the SMB protocol, like multi-channel or RDMA and so on. So reads and writes can. So reads and writes from this protocol all happen as file reads and file writes. So they look like a normal SMB read and a normal SMB write. So as promised, I would talk about error stuff more, and I'm going to do that here. So the client says read or write, and then the error the status code that's returned might be status success if it was read or write correctly. Or it could be a specific error code saying error stored. Okay? If that's the case, then it's on to the client to get extended error information, so all the sense data information, by issuing the SRV status operation with the error code with the key that's returned here. And I'll describe how that happens in a minute. And then as part of that response, this error happens here. So this is the worst case read-write path. So the read or write failed in such a manner that it's got to return extended error information. So you've got to do another round trip to the server. These reads and writes are our transformation of the underlying blocks. So like I said, these are block semantics. So the application client, so the virtual machine, will speak everything in blocks. So read 2 blocks at block offset 3, LBA 3. So the protocol will say, okay, so it's 2 blocks, and I've cached the virtual sector size here, offset, which is caching the virtual sector size here. So if, let's say the virtual sector size is a 512 byte disk, then this command of read 2 blocks at offset 3 over the wire will be read 1,536 bytes, or read 1,024 bytes at offset 1,536. And so the reason I'm going through sort of the details of how this happens is that up until now, every time there's been a command that does something to the disk that we've talked about, it happened in the SCSI world and done by the SCSI spec. So blocks, network byte order, all that type of stuff. Here, this is a file command, and it's important that this protocol, that this transformation happens in this way. So for instance, unaligned reads and writes, meaning reads and writes that are not aligned to these virtual sector sizes, are blocked and won't work. So you've got to be aligned to this. And so this is how this transformation happens.
At the client level, we expect all the requests to come at a block level. It's not unaligned. It has to be aligned by nature of being blocked. And we will translate that into a file, but it is purely to make use of SMB as a protocol.
Right. And so what he just said was, the application client, we expect everything to come at the block level. So because we translate it from block and multiply it by a block size, everything we do is going to be at a block offset. So that's fine. So as I've mentioned to a lot, SCSI has a lot of information. They've got the SRV status code and SCSI status code I've described before. Then they've got this block of sense data. And it's a variable length block that's got a sense key, an additional sense key, an additional sense key qualifier, and then maybe more depending on the server implementation of the errors. These are described in the SCSI specification, but it's a cascading sense. So for the sense key 5, there might be 10 valid additional sense keys, and for each one of those additional sense keys, there might be a valid sense key qualifier that describes, okay, so the read failed. Okay, got that from the SCSI status code. It failed because of some underlying data change. Okay, the underlying data change is continuable, and it has to do from a user disk size change or something. Okay. As I've said, reads and writes get a status code. So there are a bunch of status codes that we define as part of this protocol that mean very specific things. So here's the error stored that we know so far. Now let's talk about what these other ones are. So unit attention in SCSI world means that the client or the initiator's got to know something about what happened on the target. Okay. Unit attention available is really the same thing as error stored here, just depending on where in the server we initialize it. So you'll see different error codes there. The unit attention capacity data change. So this is a protocol or an error code that's defined that you won't see in our implementation because we don't support data size changes. Let's talk a little bit about persistent reservations. So in the SCSI world, a persistent reservation is a way of sharing a target among multiple initiators. And so there's what's called a persistent reservation table and a registration table. So each initiator can say to the target, hey, I am registering on this target, and here's my ID. So remember that initiator ID we talked about before? He's going to say, okay, my SCSI command is do a persistent reservation change, and I'm going to register. So it adds my ID in the list of registered guys for this. Depending on what the state of that target is, then that means that that initiator can do certain commands on the target. You can register, and you can also reserve. So just because you're registered doesn't necessarily mean that you're preventing anybody else from doing anything. But you can reserve the disk and say, hey, as an initiator here, I'm going to reserve the disk for exclusive access by me only. And so if I have 2 initiators, one here and one here, and this initiator says, hey, I'm reserving the disk for me only, this initiator will fail his commands. And depending on the sequence of events that led to this guy failing his commands, you'll see a specific error code here returned to the read or the write. So either this guy kicked this guy out, so you'll see reservations preempted, or this guy has for some reason released his reservation, then sends an IO. You'll see reservations released. Or, in the registrations case, something else happened where it kicked everyone else. So all of these are essentially direct translations of sets of sense data to status codes that mean specific things. And where that comes from is from the SCSI specification. Okay, any questions about this so far? No? Okay, I will say that I'm not going into a lot of detail right here. We are happy to help and understand where and what conditions these go on. I know for me, learning about, from being a file-based guy, learning about the SCSI was kind of one of the areas that took me a long time to learn and understand and make sure that I got it all right. Okay? Let's move on. So when we talk about this error storing, I keep mentioning this key and this thing here. So the error code is defined as this, C05, C all zeros. Reality, the server will return the last byte anywhere from 0 to FF. And this byte is a key into a table of extended error information that's maintained on the server. These keys are valid per handle. So when you call create file, you get a handle. These keys are valid per handle. So if initiator 5 over here has got a handle and he issues a read that fails for some reason, that we don't know how to translate into one of the status codes before, we'll return anywhere from 00 to FF as part of the status code. Then it's up to the client to say, hey, I actually want to figure out why this failed. So he'll issue a request, one of those tunnel get SRV information requests, passing this last byte as the key. So this is the final piece of that picture of how we do extended error information. And I'm going to walk through that right now. So we start from the top. Okay, read or write comes in, fails with a certain thing. Okay, returns an error code saying that it's stored. At that point, the handle there has got a table, and it's got a key into that table, which is a byte. That key comes back. The client issues another request that says, hey, get me this information. After that request happens, that handle, that entry into that table for the handle is no longer valid. Okay. Any questions? Yes, sir.
How does this work with concurrent reads? Right? You have multiple reads outstanding for each file. One of them fails, but one of them succeeds. What's the distinguishing characteristic between? Sorry. What's the distinguishing characteristic if you have multiple outstanding reads, one of them succeeds and one of them fails, on the error code mapping on the server?
Okay.
Does it make sense?
Yes. So it's on the server, it's the handle and the key returned to the client. So if the server's got an outstanding read, that outstanding read can fail.
Right.
Once that outstanding read fails, in the completion of that failure, we'll generate a key atomically, store it, and return that key back to the client.
Okay. And then just very simple question. So on the previous slide, the list of NT status codes or NT status values, are those all considered errors or any of those informational or warning, just in terms of what the server has to provide information on?
They're all considered errors in this case.
Okay.
How much detail you want to get about the errors is all different, but they're all marked as errors.
Yeah, the only reason why I ask is, at least in our implementation, informational and warning messages returned back still carry data payload or still have to carry something like the difference between invalid buffer size and buffer overflow, right? That's why I was asking.
Yeah, no, these are all error conditions. We will also return other anti-status error codes, depending on if some validation failed or if something else happened. But these are the ones that are specific to this protocol. All those other status codes sort of carry their meaning. Okay, so I've mentioned file metadata a few times here. I just want to point out a few more things about it. We virtualize some of the file metadata based on the virtual disk itself. So if you query file information, you'll see the file size or the valid data length or the end of file will all be the size of the virtual disk. So a 64 terabyte virtual disk, all these will return 64 terabytes, even if that disk is taking up 5 megabytes on the underlying storage. Okay? Another thing we do is when you enumerate streams, so that's another file information call, the shared virtual disk alternate data stream is hidden. So clients don't know about it. Okay, so that's sort of the bulk of the protocol. Before I move on, is there something, any questions? No, okay. So termination here is pretty simple. It happens through normal SMB channels. So it happens through file close. So standard, you'll see ERP cleanups and ERP closes, right? So cleanup when the handle gets torn down, close once the final handle is gone. Okay. Now, it's worth pointing out that it's up to the server to maintain enough state so that one handle closing doesn't invalidate all the other handles that are still open to the file. So 3 virtual machines will have 3 handles open to that file. Each one of them, the session is initialized and terminated independently of all the other ones. Okay, so let's talk about how we detect shared virtual disk support. So there's a specific FS control, another one, that says query shared virtual disk support. And in the response buffer, it contains shared, whether this server in this directory or however you want to define it, supports shared virtual disks. And it also returns the status of the file that you opened. So you can say, open a directory and issue the FS control on the directory. And the server will respond, hey, yeah, this computer, this directory definitely supports shared virtual disks. If you open a file that's opened in shared virtual mode, and it doesn't have to be for the alternate data stream, this current sharing status will identify that. So it'll say, hey, either this file that you've opened, some handle this file is opening it in shared virtual mode, or the specific handle that you called this on is open in shared mode. Okay? On Microsoft servers, if this FS control is supported, then shared virtual disks are supported, so we always return 1 here. Otherwise, the FS control will fail with a status unsupported or however, whatever filter or whoever in the stack would like to complete it with an error code saying they don't support it. Okay, and I just want to drive this point home. It is insufficient, so it's not sufficient just to detect server and protocol versions. Okay, so in the Microsoft implementation, it has to be on a CSV-backed scale-out file server in the context of this protocol. Right, so, I'm sorry?
How do you determine that?
How do we determine on the server that it's there, or how do we determine from the client? From the client, you drop this FS control.
And it'll error out.
It'll error out if it's not supported. Okay. Did you have a question? Okay. All right. So I'm going to point out some resources here. The preview protocol is available on the Microsoft Open Protocols preview site. As I mentioned, and as Tom mentioned, there are some changes. And so the final version will definitely include the changes for RTM. As far as I understand, the one that's up there matches what we released as part of the preview release. Jose Bajeto and Stephen Ekren gave a presentation on the scenario and some of the surrounding scenarios for TechEd. That presentation is available here, including the video. TechNet, there's a couple articles about configuring this whole setup here. And then these are the 2 SCSI specifications that I reference the most, that I think are the most helpful. And you can get those through the, I think it's the IT10 working committee. Before I get there, I want to talk about some things that are blocked. I think it's important to mention that unaligned I/O, so as I mentioned, is blocked. Cached I/O is blocked. Memory map files are blocked. There's no op locks that are allowed. Section acquisition is not allowed. Direct I/O from multiple disks to the thing is not allowed, as well as copy offload is not allowed for these files. Okay, so the server blocks all of these types of commands. Okay, now I'll get there. Any questions? Go for it.
Simply, I forgot to ask earlier, the ECP that you referenced on create, does that translate into a new SMB2 create context, or is that passed in through, I'm assuming it is.
Yeah, so Vinod's nodding his head. I think it is. I'm not an SMB2 expert, so I don't know how exactly it is there. I know that we've updated the SMB2 protocol spec to identify how this happens.
Okay, good.
Tom,
I
if you're
didn't
still-
see it
Yeah,
in the
but it's
preview
not
doc.
in the preview.
Thanks,
Not
Tom.
in the preview. Okay.
It's not in the preview. There is a new extended create context, but it's unfortunately not in the preview.
Yes, sir. Yes, so that's Vinod Shankar in the back. He's my boss. And so he's been instrumental in doing this and designing this.
Is ECP sent by the client or the server?
It's sent by the client. So in this case, the client is the one who initiates the create, and the ECP is sort of part of that create packet that gets sent from the client to the server. And it gives the information about who the client is and so on. Okay, do we have any other questions? Okay, so I think that I'm going to be around at some point to answer some questions if they do come up. I think Daryl or someone on his team will probably be the best point of contact for me, but I'm happy to come over here again and answer questions and work through some of this stuff. Okay, cool.
Thank you very much, Matt.
Welcome.